All right, welcome everyone. Thanks for coming today. Before we dive in, I just want to introduce myself. My name's Colin McNaughton. I head up engineering at NEEVE Research. NEEVE Research was founded in 2008, really on the realization that we were at a particular inflection point from the point of view of technology in which 64-bit computing was becoming ubiquitous, and dropping costs of RAM really presented an opportunity for the first time to consider application architectures that were based purely in memory. So that kind of gave rise to our core product, the X platform, which is a memory-oriented platform for writing transactional business applications that keep all of their memory in state. And the general motivation behind such an architecture is that it promotes greater simplicity from an application development standpoint, but perhaps more importantly, better utilizes hardware in a more efficient fashion. So we're a team made up of folks that really are passionate about high-performance computing and delivering architects and solutions that leverage hardware to its fullest. The platform's a horizontal platform. It's deployed on Wall Street doing high-performance trading flows with latencies that are in the tens of microseconds out to e-commerce use cases where we're not as focused on latency but higher throughputs and more complex deployment environments. So today we're talking about HTAP. HTAP's really about being able to leverage transactional data and analyze it to provide real-time insight on transaction data that's in motion, so allowing us to react more quickly to data that's otherwise sort of transient. So we'll dive into what HTAP's about in a bit more depth in a moment. But today I'm going to talk about what it takes to build out architectures that leverage HTAP capabilities, as well as discuss some of the challenges associated with achieving HTAP in real time. So we're going to walk through kind of a history of transaction processing architectures and take a look at sort of what HTAP technologies are out there today and some of the common architectures there so that we can explore some of the challenges and bottlenecks of these architectures. Finally, I'll introduce you a bit to the X platform and our take on hybrid transaction analytic processing and some of the strengths that we bring into the space. And I'll close by sharing some use cases where some of our customers and users have had great success leveraging HTAP to deliver more relevant solutions. So, without further ado, what is HTAP? Hybrid Transaction Analytic Processing is a mouthful of a term coined by Gartner in 2014, really in response to noticing new technology trends and architecture trends, emerging products mostly centered around storage technologies that leverage memory-oriented computing techniques and in-memory techniques, along with streaming technologies. So hybrid transaction analytics is all about being able to process data that's in motion, that's very timely, and allowing what Gartner calls organizations to operate on transient business moments. It's the ability to be able to identify sort of ephemeral moments based on opportunity that's present in data that's very transient in nature and act on them. So take, for example, like an e-commerce use case where we've got, we're watching as a customer's browsing through product histories, and we want to be able to take a look at what sort of items in the product catalog that user is using, and maybe be able to draw on social feeds that might give us some influence about what the customer enjoys, be able to draw from partner portals, be able to look at competitive pricing data, all of this data that's kind of very relevant in the now, be able to bring that into our transaction processing systems, the business logic that's driving that e-commerce system, and be able to present that customer with more relevant product recommendations, for example. So in short, HTAP's often about leveraging technologies that are memory-oriented that allow us to much more easily look at data in real time. But it's about capitalizing on what would otherwise be transient business opportunities. So any sort of transactional application has the potential to benefit from HTAP technologies and techniques. I think sort of the way to think about it is if you're doing any sort of transactional application, you can provide more value to the consumers of your transaction processing system if you have more relevant data to work with. So a couple of examples would be fraud detection systems, where we want to, as customer or cardholder transactions are coming in, we want to be able to look at the cardholder's recent transaction history, and does sort of the new transaction match its spending profile. Perhaps we want to send that transaction history off to some sort of machine learning algorithm and take a look at whether the spend pattern that we're seeing emerging for this customer matches other customers in that demographic. So how do we sort of leverage not just that customer's data, but sort of customer profile data that's similar to that customer and make a better informed decision? Use cases like e-commerce and retail, I sort of talked about one before where we want to provide better recommendations to customers based on both competitive data and historical data we have on that customer, and we need to do this sort of rapidly in real time with good response rates. So in short, if you've got some sort of transactional application, typically front-end logic in your application, there's a good chance that HTAP techniques have the possibility of benefiting you. So before we get in and start looking at some different architectural trade-offs, I just want to talk about some of the characteristics that we need to look at when thinking about transaction processing systems in general. And I like to think about breaking them down into sort of non-functional concerns and functional concerns. So things that I worry about when I'm writing application code, and things that fall into more infrastructural concerns, or what I group as the non-functional concerns, so not something I'm writing into business logic. So transaction processing systems, we really care from a non-functional point of view about how they perform, how they scale, and what the reliability and availability characteristics are. So those are sort of the four non-functional pillars of any application. In transaction processing systems, we typically measure performance in terms of transactions per second. That's kind of the common, my transaction processing system can do 10,000 transactions per second. But also very important is response times. It's great if I can do 100,000 transactions per second. Not so great if it takes me 10 seconds to load the customer's response page. So performance has both throughput and latency characteristics. And generally, when we're evaluating technologies that we want to use, the thing I like to keep in mind is that a high-performance system that I can do at low scale typically means that I'm going to be spending less on infrastructure concerns. So oftentimes, I can take a technology, scale it very wide, presuming the technology does scale, and that's great, but how much am I paying for the infrastructure cost underneath? Which is a nice segue into scalability. Any sort of architecture at some point is going to hit the limit, at which point I need to scale out horizontally. The underlying technology for transactions that I'm writing, or transaction processing systems that I'm writing, better be able to scale wide, particularly in this type of application where I'm trying to leverage more streaming data from outside of my transaction space. I'm trying to ingest more data in. So when we start thinking about analytics, the transaction processing plane has a lot more data inputs that it's working with. And as we're looking at more data, I'm going to be holding a lot more data in memory in my transaction processing systems. So how well can I scale out to react to load both from changing business requirements as I evolve my application, and external stimulus as external data sources spike or increase in volume, right? And then finally, sort of the simple ones, reliability and availability, transaction processing systems, they've got to be reliable, right? They're running our businesses. So I need any sort of applications that I deploy to be able to not lose requests or state in the presence of network, process, machine, or data center failures, right? So I need technologies that if a machine fails, I can fail over to a backup instance without losing any state or requests coming from my customers. Because if I'm losing requests, that doesn't really inspire a lot of confidence for my end users. So that's kind of the non-functional characteristics we're going to look at when we start looking through some of these architectures. And typically, there are going to be trade-offs, right? So oftentimes, you can do really high performance if you're not persisting at all. So it's hard to get all four of performance, scale, reliability, and availability kind of in one system. So we got to be careful about those trade-offs. Now, these types of applications, when we're talking about hybrid transaction analytics, we're really trying to leverage a lot more pertinent data in real time, right? So agility and ease of use, I think, actually, for this type of use case, really goes up beyond just sort of traditional transaction processing systems. As the business grows, we're going to want to leverage more data, connect to more data sources. So typically, we're going to want multi-agent architectures where it's really easy to drop new functionality into the application, into the transaction processing plane to enrich the overall processing in our organization. So I think when we're looking at technologies, we want to be able to write business logic in a way that we don't have to think too much about all of the non-functional concerns. So the more pure our business logic is, the faster our sort of product delivery is when we're delivering new application functionality. So, and I think I touched on it before, but intelligence, we want to make sure that these systems can really stream data in at sort of huge bandwidth and process sort of data from both inside and outside of our organizations. Okay, so with that in mind, let's take a look at some architectures. So this architecture here is kind of a simple illustrative model of what we're thinking about when we're thinking about hybrid transaction analytics. It's somewhat of a logical view that I've got up here, but in general, you've got on the right your transaction processing applications. They tend to be update intensive. So if we go back to the e-commerce use case that I was making an example of before, where we want to monitor customers' browsing habits as they're browsing through our product catalog. In this case, we might be recording page requests into the database, and then perhaps a back-end analytical process would be reading that page viewing history and running some analytics on it to look at the customer's past purchase history and maybe recommend that they buy a toothbrush if they buy one every 4 months. But more importantly, start pulling in machine learning and take a look at, this customer's browsing profile looks a lot like some other customers' browsing profiles. So that Amazon feature that says, users bought this widget after buying widget Y, right? We want to be able to sort of use collective transaction processing to surface more visible data to the user. So that analytical load now, we've got to look at a lot of that customer's transaction history, and we're potentially looking at other customers' transaction history, and we're looking in the same table. In a relational database model, this isn't going to scale at all, in part because the analytical processing is going to be holding locks on the database that prevent the transaction processing system from doing future updates, right? So if we're running these long-running transactions for analytics in the back end, we start throttling the front end, and that sort of breaks the performance and SLA guarantees that we want to meet in our transaction processing plane, namely good response times, right? So sort of the major problem with this approach is we have to kind of find a way to decouple analytical processing from the update-intensive transaction processing. The way we've done that traditionally is to separate out the data store in the transaction processing plane using an operational data store and breaking the analytics store into a back-end sort of data warehousing or analytics database. And we'll use an extract, transform, load pattern, ETL, to slowly suck data out of the operational database into the data warehouse in a consistent view, transforming it, massaging it along the way into sort of the enterprise data schema. And now we can do this long-running, read-intensive transaction on the analytical database, the data warehouse, without impacting the transaction plane, which is great because now we can serve transactions without being bottlenecked. What's sort of terrible about this is that it doesn't do HTAP at all, because extract, transform, load processes, that whole process, pulling data back out of the front end, back through into the analytical warehouse, takes minutes, hours, I mean, in some cases even days when you're looking at batch processing. So HTAP is all about being able to respond to business moments. And if it takes us over a minute to load and analyze that data, the moment's already gone. So if it takes me 10 minutes to give the customer those product recommendation, the customer's already gone, right? This architecture is great for sort of historical analysis, and it's been around since the 70s. We can take this and look at historical data and optimize the business, but totally inappropriate for hybrid transaction analytic processing. One other thing that's worth noting in this architecture is that while separating out the transaction processing database into the operational data store and the analytics database into a back-end data warehouse, we have fixed the problem of the heavy analytical load throttling transaction processing load. But what we haven't solved is how to scale the transaction processing tier. So as we scale up applications in the front end, that operational database still becomes a choke point in terms of update contention. So if I just sort of look at the scorecard on ETL-based architectural failings, one of the big ones is it doesn't scale well in the transaction processing plane. We want to be able to scale out, provide more availability in our transaction processors. But the operational data store is still a choke point in terms of updates. We've added a ton of complexity now with this ETL process. So we've kind of compromised our agility. We've got this very complicated data pipeline to get data into analytics. But more than anything else, we're here to talk about HTAP, and the main use case that we want to solve, by the time the data is analyzed, it's way too late to capitalize on it. So we're getting there. So new technologies, new advances in storage technologies, particularly leveraging in-memory techniques, has given rise to a new class of database. These databases are typically in-memory, so they give us the ability to absorb more data more cheaply and reduce the length of our transactions, right? But more importantly than anything else, it's the ability to do long-running analytical workloads in parallel with update-intensive transaction processing workloads. And typically, this is using techniques like multi-version concurrency control, where I can now start my analytical processing to look at a customer's transaction history, for example, without blocking the transactional updates by looking at an old sort of snapshot of that state that's fully consistent, starts at the time that I'm starting to look at it, but as new updates come in, they can go in on top without interfering with that analytical workload. So, leveraging this new breed of database technology, I've now got MVCC, and I'm once again able to move back towards that sort of simplified picture that until now wasn't really possible by running analytics and transaction processing on the same data store. And that's really great. This is the first sort of architecture that we're looking at here that actually would give you timely analytical results on the same data store because we've cut out the ETL process, right? So my page views come in, go into the database, I can kick off an analytical workload, either in some other process or in my own process, to sort of drive recommendation results. And I can do that in well under a minute. So that's great. It still doesn't really solve the scalability problem, though, right? So we've still got the problem of scaling the transaction processing plane up front. So MVCC allows us to do long-running analytical processing without impacting the transaction processing. But if I've got a bunch of instances hitting that database trying to update the same table, I'm still going to have lock contention, right? So we're getting there, but we're not quite there from a scalability standpoint in terms of being able to absorb a ton of data in our transaction processing plane. Where do we go from here? How do we scale out the transaction processing plane? We're seeing people adopt architectural patterns like microservices. Actually, tomorrow, my colleague Niranjan, who's sitting in back there, is going to give a talk on microservices, wave Niranjan. And he's going to go through a lot of sort of the agility benefits that you get out of employing microservices. What I want to focus on for the context of this talk is really around how microservices model says we should organize our state. And the key thing about a microservices architecture is that business functionality is organized around state that's private to that microservice, right? So we're breaking down monolithic applications into business functions that are very narrow in scope and operate on a particular piece of state. So that's a really good thing from a scalability and update contention point of view, because now it means that if my only way to update any piece of state is through a microservices API over messaging, I've now drastically cut down on the contention of multiple transactions hitting an operational data store or an MVCC. So if we can break our state out and keep it private to a particular service, then we no longer have a lot of contention for update on that state. And once I've got that state broken out, I can now further partition that state based on some sort of useful business dimension to scale that very narrowly focused microservice. So what does that look like in an architecture where we're using an HTAP DB? We can see in this diagram here that we've now striped the data. So if we model our service that's tracking page hit requests or product page views, I can now shard that service, that narrow service that's really just managing the table on customer page views, across some business metric like customer ID or the page itself. But it means that as I have more sessions coming into my e-commerce site, I can now split that traffic and scale horizontally, right? So I need to be able to scale and stripe my data to reduce contention on the database. Now, in this diagram, I'm showing two HTAP databases kind of being sharded. You don't necessarily need to scale the data tier with the service tier. What's more important is that each set of data has private state in with respect to the database table layout, right? So as long as service A partition 1 and service A partition 2 aren't intersecting in the same database, your scaling can kind of change. But ultimately, you're going to have to scale sort of the data tier and the transaction logic tier, and you're going to utilize messaging to route requests to the right tiers so that we update page view histories for, say, the right customer. So now we're looking at an architecture where we don't have any problems with analytical processing impacting transaction processing. Our transaction processing can scale by partitioning or striping our state. And we're actually looking at an architecture that's fairly viable. So this is a full-featured solution. It works, it scales, but it's not quite optimal yet. So there's still a couple challenges with the vanilla HTAP DB architecture. We've got scaling fairly well under control. We can scale horizontally by striping our data. Still a little bit of complexity we have to deal with as application architects and how to scale the data tier along with the transaction processing tier, but we can surmount those. We've got timely OLAP analytical processing analysis in tandem with transaction processing analysis. But the main sort of impediment to an architecture like this, when we think back to transaction throughputs, is that these architectures tend to feed back upon themselves, right? So we have transaction data going through the system, and we're running analytics on it and feeding it back in, and we're ingesting data from outside. So it's really important that we can ingest data into our transaction processing tier as fast as possible. And the architectures we looked at so far have one sort of glaring problem in that when we're ingesting big messaging streams into the transaction processing tier and trying to update that state in the data tier, in the HTAP database, that remote state callout is the functional, is a sort of hard limit on sort of the throughput that we can sustain for transactions when we have to stream data in order. Because before I can acknowledge a response upstream, if I want to not make sure that I don't lose any sort of transaction request, I've got to persist that data in the data tier. And that round trip time is inversely proportional to the throughput that I can sustain. So HTAP, standard HTAP architecture, HTAP DB with messaging, it scales, but it's not optimal. And what that means is that we're going to have to scale these architectures wider to be able to keep up with our transaction load. Perfectly fine, just not very cost effective and difficult to manage. So that's where the X platform comes in. So we take that last sort of mile, squeezing the performance out, reducing the scalability footprint, by allowing you to co-locate your state and business logic. So as opposed to holding state in an HTAP database, we're going to let you hold your transaction state directly in memory with the transaction processing logic. And the platform then gives you capabilities to siphon that state out into back-end data tiers, but that's done asynchronously. And the primary motivation of that approach is that it allows us to ingest data a lot more quickly. So big picture with the X platform, we have sort of two primitives that are really key to how we help you write these types of applications really easily. Is one, we provide you with the illusion that memory is durable. So we let you work with plain old Java objects in memory while you're doing transaction processing, and you can operate as if those changes are persistent without any sort of application intervention. The way we do that under the covers is by some interesting routing techniques or replication techniques that we can get into in a little bit later. The second is messaging primitives. So once we've decided we need to go down sort of a microservices architecture, which is really all about being able to scale horizontally effectively, then we have application interactions that are driven purely over messaging, which keeps us asynchronous. What gets really, really tricky in these types of distributed application architectures is how do I keep track of inbound messages that I'm processing, the state updates that I make as a result of processing those, and the outbound message delivery. Ideally, I want that receive, process, and consume to be one atomic operation. That's actually kind of a tricky problem to take care of from an application developer's point of view. There's a fair amount of acknowledgement management and state and persistence tricks that you need to keep in mind. So I'm not going to talk too much more about that today. I do have a talk tomorrow on IoT and streaming, and we'll get into sort of some of the mechanics around that. But what the X platform really gives you is the ability to write these little pieces of business logic, exposing handlers to the platform that receive inbound events, work on some state by updating it, sending outbound effects down to further stream processors, and doing that in an atomic fashion that can stream at really high throughputs, which we can do by holding all of your state in memory and replicating in a pipeline fashion to a backup. So what does that look like from a programming model in X? We give you tools to very simply model messages and state. And as part of your build chain, integrated with IDEs, we're going to generate highly efficient sort of plain old Java objects for your applications to work with. These under the covers support sort of off-heap semantics, really fast serialization, and it allows us to replicate state sort of in the most efficient fashion between a primary and backup instance, and also to communicate between processes in terms of messages. So what that means for you as an application developer is your programming model is really just writing methods that accept these message types. The platform passes in your application state, and you work with Java just like all the things you do there are persistent. So any sort of piece of state you touch, doesn't matter if that machine dies, you have a backup, you can resume processing, no duplicates, no data loss. And that sort of agility is really important in these multi-agent architectures where we want, as application developers, to be able to quickly drop new functionality into our application mix that can both respond to data coming out of our organization, doing sort of analytical processing itself, and feed data back into our transaction processing planes. So what does an X application with HTAP look like? Very similar to the HTAP database example we looked at before. Same sort of scaling pattern where we're going to partition our state, which is just objects in memory, use smart message routing that X sort of under the covers will route to the right shard. And then to integrate with the rest of your enterprise, we have capabilities to siphon out data in an asynchronous but transactionally consistent way into your data warehouse where existing analytics applications can still continue to run. And again, the key there is that state in memory now really allows us to pull data in much, much faster. So very quickly, I'll talk about reliability. We're going to talk about this a lot more in a talk I'm doing tomorrow. But the key secret to reliability when holding application memory and state is we have our processing swim lanes come into the platform. We single thread that state. We've instrumented the state objects that you're working with, so we know when you're modifying them. We can now replicate from that primary instance on the left to the backup. And what's key in X is we don't need to wait for acknowledgement from the backup before continuing to process the next event in the stream. So not having any sort of synchronous call out anywhere in the processing of that event stream really allows us to operate at the highest throughputs possible. So this we call atomic event processing. And we can get into sort of the details of it later if there's some questions, but it results in you being able to write application logic that executes once and only once. So just a quick look at the report card when using X. We've kind of ironed out the last sort of firecracker or bottleneck in the standard HTAP architecture by really allowing us to ingest data at the speed of memory. So no more callouts to a remote data grid. Everything we do is operating on local state with smart routing. Pipeline replication gives us high availability across machine or data center failures. And using a microservices type architecture with smart routing, we can scale out fully. The programming model is super easy. So we'd said at the start we want a really agile application platform where we can just write business logic and plug it in. So we're very happy with what we can do in X when it comes to these sort of HTAP loads. And I kind of breezed over it before, but I should mention it, is once you have all that state in memory, X gives you the ability to do in-transaction analytics. So it's not just concurrent analytics, but you can, while you're processing a transactional update, you can do lightweight analytics right in the transaction processing handler, right? So when I'm doing that fraud detection check, why not just look at those transactions right up front and see if the last one happened to be in New York when the new one's coming in from California. So coming to a close here, I just want to talk about some of the use cases we see out at our customers. So MGM started adopting the platform, I think, in 2012. It took them 4 months to do their first pilot project. It cost them $500,000 in development resources to really start moving some of the main reservation subsystem over into their systems. And they've been able to grow their business out for the portions running on X, so that we're putting $1 billion revenue per year through their system. So they've got a fairly large deployment, 10 services, 26 agents for fault tolerance, and they're holding sort of all that enterprise state in memory, all of the bookings that anybody's doing at any of their hotel properties, around 1 terabyte of storage. And one of the things that they've been very happy about is that when someone goes to book a room, say in Las Vegas, they can take a look at sort of the whole price book over a 14-month period, take a look at partner channel offers, and in one sort of transaction request from the browser, deliver a real value-based pricing to that customer with offers that are sort of customized to them. And one of my favorite sort of success stories is once they got sort of familiar with the platform, they put together a single sign-on storage engine. It took them 3 hours. They were able to bring this whole system up and into production, I think, in 2 weeks. So it really sort of is a testament in our mind to sort of the agility of the platform. And for them as an organization of their size to be able to operate in such an agile way. Finally, another one that's, I'd made this example before, but a company called Code 41 that we've worked with in the past built a fraud detection processing pipeline on X. Took them about 3 weeks to spin this up, but throughout this whole processing chain, they're able to look at entire customers' credit transaction history over like a year and a half, and send that off to sort of a machine learning process in the background. And they were able to push 7,500 authorizations per second through that processing pipeline, which is really cool, because when you look at sort of Visa's peak transaction processing load, what they're sort of hitting around Thanksgiving or Christmas time, their peak load is, I think, on the order of like 25,000 transactions per second. So here, we were able to run this on just 2 servers, full HA, nothing special about that hardware, and handle a quarter of their load. So that's it. Definitely suggest you check out our Getting Started guide, especially since we've just launched our sweepstakes challenge. It's win-win. You get to sort of go through, understand how our platform works. It should take about 30 minutes if you're familiar with Java, and gives you a chance to win $500 in a drawing mid-November. So check it out. Check us out on GitHub. We've got a bunch of reference applications. X applications are very easy to write, so it's pretty simple to take a look at the business logic and get a sense of what's going on. And please feel free to reach out to us contact@neeveresearch.com. We'd love to hear from you. So that's all I've got today. Looks like we've got several minutes for questions if anyone's got things they'd like me to go into more detail on. Okay, so question was, how do I do distributed transactions? So I want to be able to process a transaction that spans multiple shards or potentially multiple different services. This is sort of the case that we see a lot in X. So complicated thing to do in terms of distributed systems, and the best way that we've found to deal with that is to use compensating transactions, right? So in X, every sort of transaction that you do is guaranteed exactly once. And we can assume that if you send any sort of request that's going to span 2 shards, the platform's guarantee is that those requests are going to get processed eventually, right? So there isn't, and it's very difficult to, in any distributed system, coordinate the timing of request execution. You just don't have control over it because the shards are operating at different speeds. But you do know you're going to have eventual consistency in that transaction due to the guaranteed processing guarantees, right? Things do go wrong, and one of those shards may be down for a longer period of time. Maybe it goes down, its backup goes down, it's under maintenance. And in that case, the platform, what we've seen our customers do is the person initiating or the system initiating that transaction sets a timer, and if they don't get a response from that sort of processing, then they time the thing out. They send back to both shards a compensating transaction that said, look, this thing was aborted, we didn't hear it. So typically in these loosely coupled systems, that's your only sort of approach, is to use compensating transactions. That gets much, much harder if you don't have exactly one's processing guarantees between these agents. Once things start getting lost, things get tricky, but as long as you can have trust and guaranteed delivery, it helps you. Okay, so the question was, how do we perform backup of our data? So in the slides before, I kind of focused mostly on how we replicate state from a primary to a backup instance. The application's also journaling to a transaction log while it's happening. What's different and what allows us to operate at speed is that we don't need to sync that transaction log to disk. So we don't actually sync to disk in that transaction journal unless we've lost all of our backups, and now we find that we're in a place where, okay, we better start syncing to disk because that's our only recovery mechanism. So the backup story is you've got that transaction log. You can run change data capture on that transaction log and push it into a back-end data warehouse. So in that slide I had here where we have this change data capture flow that's pushing sort of on transaction boundaries our data into the back-end data warehouse. That gives you sort of a backup story as well. Finally, I don't have any slide for it here, but there's one other sort of data replication mechanism that we have, which allows us to replicate that transaction stream out over the messaging bus, and we use that for cross data center failure. So we call that inter-cluster replication, and for example, our customers on Wall Street will use it to, if Manhattan's bombed or something, that all that transaction stream is being funneled over to New Jersey, maybe even farther, maybe Pennsylvania, so that they can recover that transaction state in sort of like, that's sort of the data center recovery story that we have. Did that answer the question? Yes, so these journals are compacted as well. So in addition to running change data capture, we will also conflate those transaction logs. So that journal is going to look like, you know, put, update, 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 remove, and we'll conflate that down to all of the puts. We do have the ability to index those transaction logs. We don't use those indexes for recovery at the moment, but we can churn through, because the platform's zero garbage and we're using sort of flat off-heap storage, we can churn through, you know, like a 20, 30 gig transaction log and recover in like about 2 minutes. So yes, as your transaction data grows exceptionally large, recovery time is going to be a problem. So that's why we don't recommend that people completely shut down their clusters. So better to, if you're going to do an upgrade, bring down the backup, upgrade it, let it sync from the primary, and then bring down the primary to back it up. But like you say, there's definitely going to be a case when you bring that whole thing down. And so at that point, the fastest way to get data back in is from a transaction log, our journals there. If you have somehow, for some reason, lost those journals, you can also load from a data warehouse if you like to. Great question. So the question was, how do we do the smart routing? So in this picture, X has a couple different ways to do it. So you can kind of configure routing yourself. The standard way that we do it is content-based routing via pub/sub topic spaces. So to make it kind of transparent to applications, let's say in a financial services application, you might have a field on your order request called symbol. And we might be sharding the applications to process certain symbols, right? When we send that request in, as long as you're sending it in over X, we're going to examine that message and take that symbol field off and use it to construct the topic dynamically. So we can do that, that routing automatically for you as long as you're setting up that topic space. So you'd sort of define the topic space in that scenario to tell us how we should shard. Did that make sense?
So if you send the message, you can put the key inside the message, but you cannot put the exact shard number. So you have to translate key to shard number. How do you perform that?
Okay, so if you're sharding by some sort of number that's not along a business metric, so you're saying sort of some sort of hash code, for example, right? In that case, we're looking at functionality where you can use functions in that topic space that you provide so that you'd be able to do sort of something like $ hash of symbol if you wanted to do kind of the hash function for it. But right now, you have to write that sort of hook yourself. So you can provide that topic resolver.
So am I right, if you add more shards, you have to manually change
Yes. Yes, so in X right now, we don't support dynamic reload balancing, right? So it's one of those things that we don't necessarily believe in. When you're under, so when you're under sort of a stressed load, trying to rebalance state in the background, we typically see as actually exacerbating the problem. So all of our customers now kind of provision with the sort of worst case traffic load in mind. And if you do need to rebalance, then that is sort of, you have to manually push out those routing keys again. Okay, cool. Yes? So yes, if a shard goes down, and that means both the primary and all of the backup instances, then yes, the guaranteed messaging fabric we'll be buffering those until you bring the thing back up. But what's kind of key is that as you bring those applications back up, the platform's guaranteeing that there's no duplicate processing. So, but generally, you know, we try to keep enough of a sort of backup instances around so you're not, you know, zero downtime.
So do you have partial availability in the sense that while the shard is offline, the request which is routed through the smart routing logic, if it goes to the other shard, it will get processed, or it will say, hey, your part of the cluster is gone, so no processing.
So because that sharding is done over sort of a pub/sub topic space or a queue space, if a shard goes down, and that's you know, it's primary and backup instance, so there's no one processing data for that shard, then it's in the messaging fabric that it's going to sit until you bring that shard back up.
So even if the request which is coming in is for the other shard, that request won't get processed.
If it's for the other shard, then that's fine. It's going to be going to a different topic space, and the shard that's up and running is going to process it just fine.
So the partition is based on the topic space?
Yes. So, well, partition, there are a couple of different ways to do it, but the routing capability, whether you're using a topic space, whether you're using a queue, whether you're using a Kafka partition, all that you need from the messaging fabric is a way to make sure that your messages are routed to the partition that they're going. So there are a couple of techniques you can use to do that. Typically, we do a topic space that incorporates portions of that topic that are unique to the shard. So in a financial trading application, it might be orders slash, you know, symbol variable, and we'd route, you know, symbols starting with A through B to shard 1, C through D, shard 2, for example.
So if the criteria is meeting your request to be served, you can have part of the topic space.
Yeah, and we very much assume that the messaging topology is fault tolerant as well. So that needs, the messaging layer itself will be sort of a reliable messaging service that is itself replicated. So we can assume that the messaging fabric and the topic space is always available. We treat the messaging broker or messaging infrastructure as if it's a service that's always on.
So since this is using streaming,
Mm-hmm.
what happens while in the middle of the stream, failover happens in the shard? Right? Does it resume? Does it have a way to detect and hey, I did so much?
So the question is, because we're sort of focusing on sort of stream processing here, what happens if mid-processing of a stream, let's just say the sort of stream going to service A partition 1, what happens if we fail mid-processing, right? So in that case, if we fail, and if our backup instance fails, now we're no longer processing that stream fully, at least for that partition. So at that point, and it goes to this gentleman's first question, if you never bring that partition back online, then those messages are queuing up in the messaging fabric and will eventually start pushing back on upstream applications, right? So we're sort of predicated on the expectation that through high availability, you're not leaving applications sort of orphaned indefinitely.
But that is only because of, sorry, I'm thinking about it. So that's, what you're saying is a case where the partition is completely gone and it starts offering into this continuing into the next partition, right?
Yep.
I'm saying in case of a failover, like your active goes down and the backup is going to,
Okay, so I understand. So the question is, during failover, how do we sort of restart processing from where we left off? So part of what's being replicated here as part of your application state is also state about where we are in the messaging stream. So transparent to you from an application, we're keeping track of where we are in this stream from the bus, and we don't acknowledge received messages here until processing for that message has been replicated here. So that means that if we have a failover, any messages that we have not acknowledged upstream to the messaging provider are going to be redelivered. And because we can kind of keep track of sequence numbers associated with these messages, we're able to filter out duplicates on behalf of your application. So if the transaction processing results made it over, we're not going to redo that logic. Does that make sense? Yeah?
How do you make sure that you have uniqueness on the readers? So if you have a primary and secondary, how do you prevent both of them from
Going active?
or active in
Yep.
case of an exploit?
It's a great question. So when you bring up a primary or a backup instance, we have a discovery protocol that runs underneath the covers. By default, we'll use multicast, but you can drive it through messaging. When we start each instance, we have sort of a delay before they'll go active, waiting to discover other members. If there's some sort of network partition that prevents these two applications from discovering one another, then you get into that position where you might wind up in having a dual active scenario, right? And then both of these guys are going to try to create connections to the messaging fabric. So what we've done with customers, for example, using messaging providers like Solace, a lot of these messaging providers have the ability to do exclusive access to the sort of topics they're joining. So the bus itself actually gives you an extra level of sort of mutual exclusion. And as long as you can get exclusive access to the topics that you're listening to, you're good. You're never going to process a stream kind of twice. So it is possible to get that sort of partition situation. If you're partitioned from one another but can talk to messaging, then only one will go active, and it's the one that connects to messaging. The other one shuts down. If you're partitioned in a manner where you can't talk to the primary or messaging, then we don't care because your application's not doing anything. Are we out of time? Okay. Oh, I went way over. I thought we got an hour. Thank you for all the great questions, guys.